All right, for the record, this is the oral history of Jiri Marek, recorded today on the 29th of August 2017 at the Computer History Museum in Mountain View. Welcome, Jiri, and thank you very much for agreeing to donate your history to the museum.
Well, good morning, Gunter. It's a pleasure to be here.
I asked you for the interview because you are the father of the MEMS, micro-electro-mechanical systems business of the Robert Bosch company. MEMS are at first glance not very much connected to computers, but only at first glance because they are the sensors and actuators for embedded computers like those in automobiles and cell phones. But we won't restrict ourselves to just your MEMS work. The oral history is about all of you, your life and career up to now. So let's start with your background. Where did you grow up, your family, hobbies as a child?
So actually, I was born in the Czech Republic. I was born in Prague, the capital of the Czech Republic. And in 1968, the Russians occupied the country. That was still during the communist time. And our family had the possibility to move to Germany. My father, he had a research assistantship at the University of Stuttgart, and we came for vacation, for a visit. And then we've been able to stay then in Germany. So I grew up then in Germany, had to adapt to the different cultures. The Czech Republic, the border was closed. It was still very communistic, not really very advanced in terms of technology, economy, and Germany was very, very different, and the language was completely different as well. I mean, Czech is a Slavic language, so the language difference was huge, and I didn't know any German as we moved to Germany. So I grew up in Stuttgart, which is a town in the southwest corner of Germany. I went to school there, and after graduating from high school, I was either going for physics or for electrical engineering. The physics education in Germany was quite theoretical. I wanted to do something more practical. So I decided for electrical engineering, but after my bachelor, I specialized in a field what they at that time called physical electronics. So that was for me a combination of electrical engineering and physics. So I had classes on plasma physics, on semiconductors or optoelectronics. Solar cells at that time was a very hot topic due to the first and energy crisis in Germany and worldwide. With that, then completed my studies, but I had the possibility, due to the scholarship that I had by the German Studienstiftung, to go for 1 year abroad. And I did that, and I went to Stanford, so I did my research on my master thesis topic at Stanford in the Department of Material Science with Professor Bube, which was really exciting time and great experience.
What was the topic?
So the topic was I was working on solar cells, as mentioned before. That was the first wave of solar cells in 77, 78 was the first oil crisis. The prices of gasoline doubled, tripled. There was also quite a bit of shortage, so the alternative energies and especially solar became very popular. So we did both at the University of Stuttgart and later on at the Max-Planck Institute. We did some basic research to support the analysis of the materials, to improve the efficiencies, to improve the stability. And that was the topic during my master thesis.
Okay. Just for the non-German readers or listeners, the Studienstiftung is the German National Scholarship Foundation.
Okay.
I had it too. And it's
so you remember as well? Okay, good.
And it's something akin to the National Merit Scholarship, but even more prestigious than that. And the Max-Planck Society that you mentioned, I read up on this, is a non-profit corporation with 22,000 employees at 83 sites all over Germany and a budget of about $2 billion, mostly but not exclusively from government sources. So those are the two things that you mentioned.
And the Max-Planck Society in Germany is really a very big organization to support basic studies. The Fraunhofer Institute, which is also very big with several billion of revenues and also I think 20,000 people, is doing more the applied research, also lots of government contracts, more on the engineering side. So, and actually with that, that's the next step. I had the possibility to work with Professor Quaiser. Then on my PhD, Professor Quaiser has actually a very long history also with the Valley. He studied physics in Göppingen, and Professor Shockley, he got him as one of the first associates with Shockley Semiconductors, which was very much the first semiconductor company over here, which was in Mountain View on San Antonio Road, where the Pacific Stereo was. They just took it down a couple of years ago as they were rebuilding.
Yes.
And that's from the company where Fairchild started, where the six traders started Fairchild, and from there Intel started. So my supervisor was telling me at that time many stories about how semiconductors and how Silicon Valley started. So.
And later this year they'll erect a plaque where the Shockley laboratory was.
Oh really?
Yes,
okay,
it's a big shopping center now, and they'll I think IEEE and local and the museum is involved. They'll have a big plaque and I think some kind of sculpture of a transistor with three legs.
So you have to tell me when that's happening. So
yes.
I would love to see that, because that's actually the origin of Silicon Valley, even though lots of people trace it to Fairchild on Miranda Avenue, where the Fairchild Research Center was, but Fairchild was actually the second company. Shockley Semiconductors was the first one. Shockley was not very successful commercially, but he was a great inventor and a great physicist. Actually, he was too advanced. He didn't at that time. He didn't want to put transistors into volume production, but thyristors, because according to his physical understanding, which is right, the thyristor the four-layer PNP structure will have lower power consumption, because it will go to bistable state one or the other one, and therefore it should be better than the transistor, which always need a current to stay in one condition. So his ideas were right, but the technology was not mature yet, and the transistor made it, and the thyristor didn't make it. So sometimes you have to be more pragmatic and go with a real available solution to create an economic impact.
All right, so we got your PhD, and what did you do after that?
Well, I mentioned I was at Stanford. I like the place over here. We just got married, my wife and myself, and for a young engineer, it was a very challenging and very exciting thing to go to Silicon Valley. I applied to several companies over here, and I started as a postdoc at IBM in the research center in San Jose.
In Almaden?
Okay. So San Jose was a big plant for IBM doing magnetics. They had a huge operation with many thousand people. And actually the research center was down at Cottle Road, and a year after I left, it moved up to Almaden. Okay. So that's the Almaden lab, but it was at that time still incorporated with a manufacturing plant, which was then sold off later on to Hitachi. And after the postdoc, I looked around and I started a job as a development engineer with Hewlett-Packard. I was working on reliability of LEDs and detectors in 3.5 technology, mainly aluminum gallium arsenide. That part of HP became Agilent, and that part became Lumileds. We started at a building on Page Mill and El Camino in Palo Alto.
Oh, okay.
Very close to HP labs. So because at that time it was very young technology, so we had to do lots of basic research and lots of testing. So I was going to HP labs for some measurements, for some analysis almost every week or even more than that, which was very nice and convenient. And then as we've been expanding, I mean, at that time, HP was doing then huge investment to ramp up the volume manufacturing. Also in Singapore, we started a wafer fab and the assembly in Malaysia, in Penang. HP at that time was #1 company in LEDs, huge growth, very high tech. And we expanded into a new building which we built on Trimble Road in San Jose, close to the airport.
Which is
and
where
that's where the
now.
building actually still is. Lumileds wanted to do were supposed to be bought by a Chinese company, but the Obama administration objected due to cartel laws. And now I think it's owned by some American investment company.
Okay.
Well, with that, we've been around for a couple of years in Silicon Valley. So that was my second stay in Silicon Valley. For my wife, the first one. But after 4 years, and the border was still closed to the Czech Republic, that was still the communist time. Our families, since we are both from the Czech Republic, were in Germany. We didn't see them for a long time. And we decided to move back to Germany to start a family. We then got 2 daughters, which we raised in Germany. So
what year did you go back?
Excuse me?
What year did you move back?
I went back at the end of 1986.
Okay.
And so I interviewed with various companies in Germany as electrical engineering, main companies in southern Germany, being Siemens, Infineon, also HP, Bosch, IBM with the research in Reutlingen. Google has a lab now also in Switzerland, ABB. So there was lots of high-tech industry interesting for electrical engineers. Bosch made me an offer because at that time there were the first structures made in silicon by MIT and also researchers at Berkeley. So what they were using the standard silicon wafers, and they used the polysilicon, which was used for the gates of the transistor. They etched away selectively the oxide. The oxide was the gate oxide. And they were able to do moving structures out of this polysilicon. So they had very thin polysilicon layers. They made them free, and they made small wheels, moving structures, bridges. So there was the first steps of micro-machining, or MEMS, the micro-electro-mechanical systems, as people call it, where they were able to do the first moving structures. These were pretty much academic, not very much of an application. But it was exciting technology, and the manager, the executive vice president at the electronics division of Bosch thought, this is something exciting to combine mechanical parts with electronic parts and use the same technology, the semiconductor technology. And as the semiconductor technology was making so great advances of making things smaller and cheaper, and really increasing the performance, he thought, it would be very exciting for Bosch as a company involved in many electrical but also mechanical systems to combine the technology and to develop it and to have a look if it has some applications for Bosch. So he hired me in December of 1986. I spent 1 year as a trainee to learn about the division, about the development department, about the manufacturing, to learn the technology. So I was going through the different departments, about 6 weeks, 8 weeks in design department, simulation department, layout, manufacturing, testing, to really learn the basics, how the whole industrial operation was working. And then after a year, I became a group manager to set up this technology. Well, to make the long story short, I've been responsible for that for quite a while. It was 25 years. After 6 years, we started production with the first sensor, which was the manifold air intake sensor for our engine management system, which is a device like this in a really metal can package, because it has to be under the hood. It gets the exposure to very tough media, the air coming inside with salt, spray, chemicals. You wash the car, right? You go in Nevada through dirt roads, so it has to be very robust. And after 6 well, very exciting, but sometimes very tough years. We made it to volume production.
Okay, that was one of my questions. How long does it take?
It took
from
quite
zero?
a while because the automotive industry is a very conservative industry for a very good reason, because we are making systems which are really, as the Bosch motto is, invented for life, right? I mean, you have an engine management system, it has to accelerate. If it doesn't do that, then you might not pass the car, or it will stop in the middle of the freeway. We do with those sensors braking systems, we do airbag systems, where you really have to rely on the performance of the sensor, of the system, of the complete electronics, sensor and actuator system to really actuate. And if there is some fault, it might put you really in danger and really even not save lives, like in airbag or on braking systems, really put you in very dangerous situations. And therefore it has to have a very high reliability. At the same time, in the automotive, we have a very high temperature range, going all the way from minus 40 degrees C all the way to 125 degrees C or even 140. If you imagine you have a car in Alaska, in Canada, then you have to start it up also when it's winter and when it's cold. So you rely on that system also under that condition. If you park your car in Arizona inside the compartment, it will get 80 degrees Celsius, 90 degrees Celsius. But if you are under the hood where the engine is, the engine obviously being a combustion engine gets very hot. So there we have conditions of 125 degrees C. And if you even put electronics on the braking system, if you are driving a car and the braking systems, the hydraulic system are close to the engine, so they get also pretty warm. But when you go 100, 120 miles an hour and you do really a full braking system, there's a lot of energy which gets dissipated in the braking system. And we have peak temperatures going all the way to 140 degrees C. So that's very high demanding ambient. We also have electronics which are integrated into transmission system. So the electronics is actually inside the transmission, and it's inside on the side of the fluid, of the transmission fluid, and that gets also very hot. So we have a very high temperature range. We have also very long operating time. Cars are pretty reliable now, but that means also that they will be on the road for 10 years. Generally, a laptop, a smartphone doesn't last 10 years, right? And you don't expect that. And even after the car is older, you want to have some spare parts. There are lots of old timers which are 25 years old, and they still have to be on the road. So we have very long times being in the field for operation. Then, as mentioned before, you go and you drive the car off-road, so it becomes very dirty. You have sand, you have lots of particles going into the engine, onto all the electronics. Then you wash the car, then you have detergents, you have different fluids, so all the electronics have also to be stable. So we have really very demanding conditions, which are very close to the aerospace or military applications. At the same time, the costs have to be very low. And that creates quite a bit of pressure onto, well, the cost, but the technology and the reliability. And therefore the automotive industry is more conservative in terms of applying the technology, because we really have to be about factor of 10 or 100 lower in the failure rates than consumer. If you've got this morning in the car and you started driving, in the case your phone had some problems, then you are pretty angry. But on the way home, you will stop by at Verizon or T-Mobile or AT&T. You will get a salesman. You will be very angry. They will give you a replacement phone, and they will give you a $20 or $50 voucher, and you are happy, right? But if you start the car in the morning and it's not going anyplace, you get real angry, right? You don't get to work. Your boss is angry at you, and so the consumer electronics and the automotive electronics, they have quite a bit of different expectation also for us as the customer, and that creates quite a bit of different reliability levels of that. And therefore, the automotive industry has generally a fairly long qualification cycles. So from the design, where we really did the first design verification to ramp up of high volume, it takes about 2 to 3 years, depending on how novel, how demanding this technology is. Because we have to deliver, we have to put in the production line in place, which is capable of doing 100,000s or millions of devices. Then the car companies will put it on a new car, on a new platform, but they will take those cars and they will test the whole car inside their labs. They will do crash testing but they will do also lots of track testing. In the summertime, they go to very hot places like Death Valley, which is very popular for car companies to do the testing in the summertime. And there you have, 50 degrees Celsius, 140 degrees Fahrenheit, and they do testing under those conditions.
So does each car company have to do their own qualifications, or is there a body that can qualify a type of sensor that then everybody can use, or do they actually want their own model, their own tweaks on a sensor? The different car
as
companies.
mentioned before, they do the summer testing in hot places like Death Valley. They do winter testing, in Canada, in Europe, it's done in Sweden. They rely on qualification testing that we do as a Bosch. So we would have a sensor being for pressure sensor for engine management, or airbag sensor, or one for vehicle stability control, which is the guy over here. And we will do qualification according to industry standards, which are set by the different bodies. But some of the customers also, they demand additional testing. So on the component level, we will do a testing. We have to show the results to the car companies, and then they will either approve or they will require additional testing, and they will check those results. Then these sensors, being sensors and also actuators and electronics, they go into the electronic control unit, into the system. This system is then put on the car, and the car companies will then do their testing on the overall system. So they assemble the car as the prototype. So they put the engine management, the braking system, the vehicle stability, the body control, navigation, all the systems which are required. And now there is a couple of dozens of microcontrollers and computers on the car. And then they have to test it under those conditions. And they also test, the performance of the car overall, how the systems are communicating to each other, if the systems are performing well, as the combination of them. And they also have to set parameters. Each car has a different dynamical performance, right? How it's handling in the curves on the braking. So they have to adjust the parameters for the vehicle stability control to set all the parameters to really perform in the best way. And the same thing for engine management. So there is a ECU, the electronic control unit for engine management, which companies like Bosch will deliver. But then the car manufacturing, the OEM, he does his software and the parameters to adopt this system to his engine, being a 2.8 liter 6-cylinder engine designed for this car. So they have to do all the testing then on their own, and with those results then they go to the certification companies and obtain approval from them to put these cars then on the road.
Okay. So, and going back to you were building up the MEMS department or subsidiary. In those first 6 years, or at the end of the 6 years, how many people did you have working, starting from one?
So I started pretty
right?
much from scratch in 1988. I started then as group manager, as Ben mentioned before. Then 4 years later, I became department managers. I think at that time I had about 3 groups, and we had about 30 to 40 people. So on those sensors, we did everything. We did the mechanical design, because it's a mechanical system, how thick the membrane is, where to place the resistors, how wide it is, how thickness of the wafer is, how to do the assembly. We did the layout, like on the integrated circuit. So we did the process development for the micro machining part, to really etch those small structures into silicon. Then we did the assembly, the testing. So we developed both the device and also the process technology, and we worked very closely to the manufacturing guys, because when they hit then the bottom, let's start the production, they had to deliver suddenly a couple of 100,000 with excellent quality and excellent performance with these requirements to the customer. So that's about the size that we had, but we had also lots of support from manufacturing people and application people within the Bosch corporation to support that activity.
Okay, so you used existing manufacturing plants?
Yes, we used the manufacturing infrastructure, but we had to do and develop some of the processes which are special, both on the semiconductor, on the wafer part, also testing, because we had to test for pressure, which you don't do with integrated circuits. We had to do a special assembly to put it into a package which goes into that. So we used the infrastructure, the manufacturing process guys at the plant, but they had to adopt quite a bit and do quite a bit of changes. So we worked with them very closely as a simultaneous engineering team. So we had a simultaneous engineering team, as it was called at that time. We put the development engineers, the manufacturing engineers, the quality engineers into a special project room where they worked separately from their home departments. And that's where they developed and ramped up the volume production for the sensor about the last 2 or 3 years before the start of production.
So how different would you say is the, how many steps are different from, say, making a power electronics device, which Bosch had been making for a long time? Like in percentage of steps that you had to develop?
So if you look at the wafer side, I would say about 80% is really based on the semiconductor process. 20%, perhaps 30%, depending on the device, is then done separately. As we do the testing, we go on to standard wafer probers, wafer testers, so we are able to do that. But we have to change the handling a little bit because the structures are much more brittle, much more fragile, so we have to handle them with a little bit more care. So in terms of wafer testing, it's perhaps 10%. In terms of the packaging, when you go to package, then obviously we have to go for special packaging, like really going for automotive type of package. And then the packaging becomes very different. So on the final package side, I would say that's almost 100% because not very much of other equipment can be used. So to do the packaging and the final testing before it gets to the customer as the plastic package with the connector, with the pressure port, then it's really 100% dedicated.
Now your MEMS devices, I assume in many cases displaced previous technology, larger, like there have always been pressure sensors in the car, right? And they were like vacuum cans or something like that.
Exactly, yeah.
So was there some friction of the established departments?
Yes, there was a little bit of friction. So in terms of the sensors in the car, as you mentioned, the first sensors to make electrical and then electronic system were mechanical. So like for the pressure sensor, there was a really, like metal container cavity, and the pressure as it was changing, it changes the volume, and the volume change was picked up by a Hall sensor. Also for acceleration sensors, there was a mechanical structure which was a metallic beam, and the beam had a weight which was soldered at the end, and there were piezo resistors in thin film technology, and they were moving it up and down, and those were the first acceleration sensors for airbag, which were used, I think, in 1984 to make the first airbag sensor, which Bosch and Mercedes put on the market. Unfortunately, I don't have those samples with me. They are in Germany. And then this technology was changing and went into actually as an intermediate step into hybrid technology. So at that time, because of the high temperature requirements and reliability requirements, people used the ceramic substrates. They printed thick film resistors on it and conductors. And then we were also making sensors based on this. So the second wave of sensors was then hybrid sensors. So what they used is a ceramic substrate. They printed different layers. And there was also a layer which was carbon, and the carbon got changed, burnt out at high temperatures and created a cavity. And the change on the cavity between the substrate and this bubble, which was sort of on top, was picked up also by piezo resistors. And for the acceleration sensor, we used the ceramic substrate. We would put a piezo resistor beams, really piezo ceramics, assemble them on top. And during the crash, they would be bent due to the seismic movement of the mass. And the piezoelectric materials have a very high charge generation during mechanical strain, and this charge was picked up and amplified and went then into the electronic system. So it was the mechanical systems in the 60s, 70s, then the thick film technology, ceramic technology, and then it went into silicon. And obviously, with all of these generation changes, there was a little bit of friction. Always the old technology tries to push the performance and to lower the cost as much as possible. But by the end, you can't beat the new technology, economic and performance-wise. So it was a transition over a couple of years before all of these generation came. So in terms of the electronic systems in the car, I would say the micromachining was the third wave after the mechanical system and the ceramic thick film, the thin film or the semiconductor-based silicon technology for the sensors.
Were you at the beginning, were you worried that you could achieve the reliability? I mean, the hours of operation aren't so very long, right, for a car, but the environmental conditions are very harsh.
Yeah, exactly. So the car will be driving for 3,000 hours on the average, but it has to have a very long lifetime because it will be on the road for 10 years, 12 years, 15 years.
Which matters for contamination and things.
Exactly, right? Yes. And also for long-term stability. So yes, we are very much worried about all the aspects of this technology in terms of reliability, long-term stability, offset performance, and all these things. And as the technology was pretty new, we actually also did quite a collaboration with universities or Fraunhofer Institute or Max-Planck Institute and did some basic research. So we were looking into, as we introduced later on, the polysilicon. We were looking into the material properties. What's happening with the polysilicon? If you stress it, are there changes in grain boundaries like there are on metals, on steels? Is the doping changing over lifetime? Will the doping segregate and the boundaries? Will it change the mechanical properties? Silicon is an excellent mechanical material, and the single crystal silicon which is used for semiconductor, it's one of the best studied materials in the world with excellent quality, with purity which is really extreme. I don't think there's any other material in the world which you can obtain at such a high quality, quantity, performance, and purity at this type of cost. And therefore, there's lots of information about that, but most of that information is on the electronic properties and not on the mechanical properties. And we also use polysilicon, not only the single crystal, and therefore we studied the mechanical properties of polysilicon. So we gave out a whole bunch of these topics to universities, to Fraunhofer, to study these questions that we had about stability of resonators, of grain boundaries, polysilicon over lifetime, over lots of periods of movement, of acceleration, over stress, and all of these type of things. And there were a whole bunch of Ph.D. theses that we did together with those institutes to study the basic properties and to really achieve the performance and reliability which is necessary.
And so nowadays you're confident to predict a lifetime from, I guess you do accelerated life tests on your
Yes, we do a lot of
right?
testing, and we have lots of knowledge about the material also in terms of the mechanical properties. And now we have a very sophisticated design process. And at the same time, we've got lots of data from the field. Bosch last year was making 1.4 billion sensors every year. Accumulated, we did 8 billion sensors which are in the field, and we have lots of data on those sensors. So we really know by now that all the predictions that we did are really becoming true, and that for our models, our material knowledge, our design coefficients are really performing well.
So how many sensors are in a car of 2017 model year?
So a typical car nowadays would have about 50 sensors.
50 sensors.
Yes, it's amazing.
So that includes airbags and things, right?
So well, the car is driving, right? So you have the drivetrain, the combustion engine, and on that you have a sensor to measure the air intake. So depending on the oxygen that you are taking in, then you can inject the fuel. That's either a pressure sensor or it's an airflow sensor, which measures the airflow coming into the engine.
How does it do that?
Excuse me?
How does it do that?
So, well, that was the next set. After pressure sensors, we did airflow sensor, because the airflow sensor is very accurate in terms of the measurement of the air mass of the oxygen that you are taking in. So for that measurement, we created very thin membranes, but the silicon is also a very good heat conductor, and therefore it would not be very good to measure the airflow. So we created a membrane which is etched out of the silicon wafer, but it consists only of oxides and nitrides. So we really take away the complete silicon, and we create a membrane, a bridge with oxide nitrides. We have to stress compensate it, because oxide and nitride have a different expansion coefficient compared to silicon. And we put platinum thin layers on top. We manufacture a heater on the surface. We create a temperature increase, which is very local. And due to the air flowing over the chip, this hot wire, this hot platinum wire, gets cooled down. It transports some of the heat downstream, and therefore we can measure the temperature on this heater. Okay. We can measure the transport to the right, which there is a temperature increase, and there will a temperature decrease on a temperature sensor on the other side. So we can also measure very fast, because it has a very low thermal capacity, the direction of the flow, which is very important, because the sensors in the past were very slow. And on new engines, if you have a 4-cylinder downsized engine with 2 valves, 4 valves, there is even a backflow. And the sensors were very slow in the past, so there would be a air intake. Due to the valve timing, there would be a little bit of a backflow, but the sensor, which was very slow, didn't detect it. So it was actually detecting the
sum of the two.
The sum of them two, which
the
is
absolute
wrong.
value sum.
So the electronic management system for engine management system was getting the wrong values. It was injecting too much fuel or too less fuel, not enough fuel, and therefore it didn't have the appropriate combustion. And that was in the 90s that we've been able to do prototypes, and car manufacturers were very much interested, because our sensor was very small. It was a very fast sensor, and therefore they could detect the airflow and the profile of the airflow very accurately, including this back pulsation. And therefore we could get very accurate values of the air, of the oxygen, which is going inside the engine, and therefore we could improve the combustion. And with that, not only the combustion, but also the emissions and the economy, the fuel economy of the car. which was very interesting to the car manufacturers. And so after the pressure sensor for engine management, the airflow sensor in 1995 came to volume production because that was a very interesting device for that application.
Okay, and then I guess you have all kinds of inertial sensors.
That's right. We have all kinds of inertial sensors. Well, the first were the airbag. The airbag came onto the market in the 80s with a mechanical sensor that I described before. But then the electronic systems had to be cheaper and smaller, and therefore we came with acceleration sensor made also by MEMS. For that, we take the silicon wafer. We etched on the surface structures, which are COM structures facing each other. And due to the acceleration, they will move. One of the structure is really fixed to the substrate very rigidly. Mm-hmm. The other one is flexible, and therefore during air crash, it will start moving this way. And as the fingers are moving, then there is the distance difference, and that's capacitance, right? And with a capacitance change, that's very easy to measure electronically. And with that, we were able to manufacture acceleration sensors, which were very small, very reliable, and also very cost-effective for airbag. Then after airbag, it was the electronic stability system, which is a system which improves the stability of the car in critical situations where it's very close to skidding. So the ESP, the electronic stability control system, is controlling the dynamics of the car. It's measuring the steering wheel angle, and the steering wheel, that's the wish of the driver. Do I want to go right and left, and with what kind of angular speed I want to do that? We are measuring the pressure on the wheels, the braking pressure, and we are measuring the rotation of the car according to the perpendicular axis of the car. And then the system is comparing the steering wheel angle with the rotation of the car. If it's really driving into the curve, as the driver, if I put my wish onto the system. So if you are skidding, if there is ice, if it's raining, if the conditions are very bad, and I've been driving into the curve way too fast, I would start skidding. Then the steering wheel angle and the angular motion of the car is different. And then the system will put different pressures on the front wheels and the back wheels, to also different on the right and left. And then it will correct the car and put it back again on the path which I, as a driver, with a steering wheel, which I'm commanding. And it's really amazing. These systems, under critical situations, improve the stability drastically. They cannot do more than the physical limits are. If it's really icy, if it's the friction is very low, then they cannot do it. But they can do it much better than any kind of human can do. And therefore, in critical situation, they can improve the stability. And we worked very closely with a European agency, but also with US agencies, with NHTSA, and we've been able to verify that such systems are making an improvement, which is saving thousands of lives in the US only. And therefore, with the introduction of the system in the 90s, this system's really saved quite a bit of lives, both in the US, Europe, but also in Asia. These systems are now compulsory in the US, in Europe, in Korea, Japan, and also coming in China with a 100% requirement.
And I assume the laws of what exactly is required are based on what you say you can do, right, in terms of what's technologically possible.
Yes, so obviously the experts with the automotive companies, the expert with Bosch as the supplier on the electronic system, on the mechanical system, we can show what the possibilities, what the limits are of the systems. And then we are working with regulations agency to show them these systems possibilities, but also limits. And then we try to work, and I mentioned before, Bosch motto is invented for life, to really improve the stability of the systems in a way where we can make the cars safer, but also improve the fuel efficiency and also the emissions. So in order to give progress and give back to the society in terms of the performance of the system.
What's the response time of, say, the stability control system?
So the stability control system, it will do measurements and do updates on the order of milliseconds. The braking systems, I think, are on the order of about 10 milliseconds. The airbag systems also have to make decision in this. In the case we have a crash from the front or from the back on the order of 10 milliseconds. However, if we have a crash from the side, these systems have to react faster because the crash is progressing very fast towards the passenger, towards the driver, and then we have on the order of just a couple of milliseconds to make the decision. So these systems have to do and work really at micro-second scale. We have to go take the data, we have to update the data, we have to calculate the data, make checks that the data is really stable data before making a decision, because if you blow up an airbag, it will deploy. And if you deployed it and it was actually an error, you don't want to have an airbag blow in front of you on the freeway. That's not a very good condition either. So both situations, deploying too early or too much in a condition, but also not deploying or deploying too late is not very good for the driver, for the passenger. So we have to really deploy it at the right time.
So the sensor itself is reacts on in the microsecond scale?
So the resonant frequency is on the order of a couple of kilohertz. So we can measure really up to a fraction of milliseconds.
Okay.
And we provide data then on microsecond scale for the system, because we have to do all the calculation and checks.
And so each airbag has its own sensor?
Well, actually, each airbag sensors, each airbag system has quite a bit of sensors. So really high-end airbag system, it will have electronic control unit, which is generally mounted someplace in the middle of the car, because we want to take the movement of the car as the whole body, right? Because you can have a crash from the front, from the back, from the sides. So we want to have it at a fairly rigid place where it's well coupled to the car and receives the information from all sides in a very precise but also timely manner. It will have a safing sensor, to redundancy sensor, to check if that's really true. So it could be that the sensor has some kind, it's blocked, or it might have some electronic error, or it went wrong. So for reliability reason, there's a second sensor as a redundant sensor, and control is always checking the signal of one and comparing with the other one, and checking for plausibility, and to say, well, yes, my system is performing well. Then we have sensors in the front, because if you have a high-speed crash, you have to react fast. So you will have one or two upfront sensors, which are also assembled in a very rigid way and placed in front of the car. Then for the side crash, it's important to react very fast, because you've got only about 10 inches, 15 inches from the body of the passenger, of the driver, to the door, to the first impact. And at the same time, if there is a side crash, our body is built in a way where, you know, if you have some kind of crash from the side, then the injury, the neck injuries are pretty severe, because your head will move to the right and to the left. And therefore we want to deploy the side airbag sensor and the window bags and the side bags very soon, to protect the customer in a very reliable way. And therefore we have only a couple of milliseconds to make the decision, and we place side airbag sensors to the right and to the left. And if we have a bigger car, we have them on the driver and the passenger in the front row, but also in the back row, and in some of the vans, even the third row, to protect all the passengers. And there also, if you have a rollover, which is if the car is going down into a ditch and will roll over, if you look at that movement of the car in terms of the mechanics, there is not really a crash until you hit on the roof, right? Because there is no impact on the body. There's only this rolling over movement, and then you have a very severe crash, either to the side or even to the roof, and then the injury would be also very serious to the passengers. Therefore, we have a rollover sensor, which is a yaw rate sensor, an angular rate sensor, measuring the movement of the car along the driving axis. And if that movement becomes too high, then the airbag system will deploy as well before actually the so as you see, it's only the airbag system, but we can have dozens of sensors connected to the system to really protect the passengers in a very reliable way under all the conditions.
And those sensors they are not in the airbag assembly. They are on the chassis, and they talk to the central airbag system.
Yes, so there will be the central sensor. There will be the redundant, the plausibility sensor, also in the ECU in the center. The rollover sensor, this angular rate sensor, is also in the middle car of the car, because the whole car is moving. But because of the very fast timely dependence of the crash, right? We have to have place the sensors really to the outside. So there will be one or two in the front. There will be the ones to the side, and they have to be deployed really on the side or in the front of the car, and they are connecting with the wiring to the airbag control unit, and that control unit is making the decision, and then it's giving the signal to deploy the airbags. And the modern airbags systems are also very sophisticated. We've got the passenger and the driver, which are inside the steering wheel or on the dashboard. Then for the side impact, we have one on the side for the shoulder. We might have a window bag which deploys from the top. And on some systems, even a sensor for the knee, because the knee injuries as you are moving forward can be also very serious. And then you have also bags for the knee injury. And the same thing can be also for the second row, where you have a side airbag sensor for the passengers in the back row to be protected. So as you see, those sensors systems are quite complicated, with lots of actuators, lots of sensors, and lots of electronics.
But a central control unit that makes the decisions.
Yes.
It's not the bag senses itself, it's being accelerated and it blows up.
Yes, so the computing is done in the central electronic control unit. The sensors will have a little bit of intelligence, so they do the signal amplification, they do some plausibility checking, so they really provide some additional signal evaluation within the sensor. And the new sensors will provide the information via a digital communication, so we have a secure communication to the control unit.
And so that's electronics integrated onto the sensor chip.
Yes, there's quite a bit of also evaluation and electronics for the signal.
Okay, so I looked at the list of your patents, and I see basically 4 broad areas: acceleration sensors, force and pressure sensors, valves, and mass flow sensors. Does that about cover what Bosch does, or are there others that
so for the
you didn't work on?
automotive, it's as you mentioned, it's the pressure sensors, both for air but also for fluid like braking fluids. It's acceleration sensors for airbags, as we discussed before, but also for acceleration like navigation systems to measure the acceleration, the braking of the car. the yaw rate sensors for stability control, but also for navigation. We use gyros. Then we have the airflow sensor, as mentioned before. The valves didn't make it to volume production because the ambient conditions are very, very tough in the car. And in terms of the performance and the reliability, the requirements are so high that we were not able to really make cost-effective systems to do all the protection. The silicon is very brittle, so in order to withstand to particles in fluids or in air, it becomes very tough. And if you want to do an actuator, you need big forces to move the things. And then the devices are too big and not economical. So the valves didn't make it in the automotive to volume production. But in medical, there are some silicon structures in the medical field where people are very interested in handling very small amounts of fluids, like insulin for diabetes. And so those applications are being then follow up in that field.
Okay.
And didn't talk about that yet, but in 2005, we created a completely owned subsidiary as a startup called Bosch Sensor Tech to serve the consumer electronics field. So in the early 2000s, we looked if there are some additional markets for MEMS structures besides automotive. We looked, did a business field analysis. We identified two possible fields. One of them is being bio, analysis of fluids, gene sequencing and handling very small amounts of fluid analysis for bio applications, and also the consumer. That was in 2005. To remember, the iPhone just became 10 years old, right? So it was 2007 that the iPhone came onto the market. At that time, it was Nokia and the other companies which were dominating the market, and we still have quite a bit of different phones than the smartphones nowadays. But still, they were starting to use sensors. They were starting to use sensors for changing the portrait to landscape orientation, to switch on and off the display as you move the phone, to use it perhaps for navigation in the future. So the phone became really smartphone at the time, and in order to be smart, it needed to interact with the environment, and therefore it needed also sensors for acceleration, for gyros, and even now we are using sensors to measure the ambient, the pressure, so we can measure the elevation due to the atmospheric pressure, the change in weather, humidity, air quality. So even those sensors are now used in the car. In the smartphone. So in 2005, we started sort of an internal startup, a subsidiary of Bosch, but really focused onto the consumer. We had quite a bit of discussions if we should do it within the framework of our division, but it was automotive electronics, very focused on the special requirements on the automotive, and we decided that we will set up a separate team, even a separate company, to serve this consumer field in order to serve the customer better. And now Bosch Sensor Tech, 2015, they celebrated 10 years. We are the largest manufacturing in the consumer electronics sensors for that, and really? Overall, we are the top manufacturer of MEMS devices. And 70% of all the sensors that we produced are now going into consumer. There's billions of smartphones manufactured worldwide, and all of them have a Bosch sensor, pretty much. So we are very happy to serve the smartphone manufacturers worldwide and provide these very important components to them.
And they presumably are easier to make and smaller because they don't have the same reliability requirements, right? People keep their smartphones
they
for a couple of years.
don't have the same reliability requirements, so you might think, well, these are really much easier to be manufactured, but the problem is that the consumer electronics has much higher pressure in terms of the pricing, because those devices have to be much, much cheaper in order to really go. They have to be much, much smaller. If you compare it, we have some gyro some acceleration sensors, and they've been, you know, when we introduced them on an order like this, now the acceleration sensors for airbag might be something like this, but if and the devices for consumer field, we are even this size.
It's not that much easier because of the price pressure, price and size pressure.
Yes, the requirements are very high. We have still to deliver very high resolution signal. So the requirements on the acceleration sensor and on the yaw rates are also very demanding, because we want to measure a very small angle with a phone and with a gyro as well for navigation, for indoor navigation, outside navigation, to supplement additional signals to the GPS. They have to be very small, so the mechanical structures are very small, but the resolution has to be very high. The cost, as mentioned before, has to be low as well. And last not least, the power consumption has to be very low, because if you have a smartphone, you don't want to drain the battery, so we have to decrease the power consumption quite a bit compared to the car, where you have a car battery and really also some power consumptions on the power electronic side. So the power consumption is not that much of an issue compared to the, you know, mobile devices. And that creates completely different set of requirements and also different designs. And therefore, we have a separate organization to handle that in order to provide devices to that market.
So I assume you will try to integrate as many sensors as you can into one device, right?
Exactly. So actually, what is now on the smartphone is what's called an IMU. That stands for Inertial Measurement Unit, and the Inertial Measurement Unit is a combination of a 3-axis accelerometer, because the smartphone can be held in any direction in the space, and also a gyro in all 3 directions, because you can move in the space in your room and navigation with a phone in all different directions. And so we have really a complete inertial measurement unit, and that measurement unit is also going into these small devices with accuracy which is really incredible at a very, very low cost. So those designs are very challenging, and we have many engineers working on that to make it happen.
So I found 27 patents of yours, which were the dates kind of end in 2005. Is that when you moved well, away from the actual technology?
Well, thank you very much for for researching into that. You know more than I do. I didn't count on that exactly. Yes, I became you know, department manager in the 90s. Then I was vice president and senior vice president at Bosch, handling an organization of several hundred development engineers and several hundred million in terms of revenue. So I was very much busy really into management, this innovation and the organization. And I had a staff and a structure to really work on the details, and my associates then did the major inventions. I did the impulses how to do that, but obviously the detailed invention were done that way. Bosch overall, as mentioned before, we are a MEMS pioneer. We were one of the first companies to go into the market. Now, according to the market research companies, we are the largest manufacturer with over 1.2 billion of revenues, and we have over 1,000 patents in that area. So
okay, that was a
quite a
question
bit of basic research in order to put this technology into volume production. And if you look at it, you know, with 25 years of experience in that field and several hundred people, there's many thousands of man-years of development which went into those MEMS systems.
Okay, we should mention that in 2008 you were awarded a future prize by the President of Germany. Can you talk about that or show us the prize?
Very happy to do that. So in 2008, we were able to receive this prize. It's very heavy. It's really basic steel, and the symbol. It's not that well known outside of Germany, but this is sort of the scientific Oscar in Germany. So 3 teams can apply, 3 teams which are working on some new technology, but technology which is really relevant to industry, to manufacturing, to the society, and has been really verified and put into production. So, and those teams, they apply. There is a TV show on one of the major networks channels in Germany, which is at prime time about 3 weeks, 4 weeks before Christmas, with a very famous moderator in Germany. And the 3 teams, they pitch for their innovation. And at the end, the president receives an envelope which has the winner. He doesn't know who the winner is. And then he opens the envelope, and the winner for this year is this and this team. And so we applied in 2007. We've been invited 2008, and 2008 then we've been invited to this TV show. So it was a very exciting event to be on TV with 5 million or 10 million people watching you, and you don't know what the outcome is, and you are in front of the German president. So it's like being on whatever ABC or CNN and receiving an award from Mr. Obama or Mr. Trump. So that's quite a event which we went, and we were very happy that our technology, our contribution was really acknowledged with this award.
Congratulations. Yeah.
Thank you.
So this is not for research, but for technology that is proven in industry.
So it's really for innovations which really are proven and went into, or just in the process of going into some industrial. So it's not like a Nobel Prize where it's really pure research. It doesn't have to be application. It has to be a major innovation which is applied to application and is just starting with some applications or production, or has already entered the first couple of years of production.
Okay, and so what is your growth prognosis for the MEMS industry in terms of volume, but also are there fields that you see it going into that are not covered yet?
So looking at the industry, both from the electronics industry, we have now about 7 billion devices connected to the internet, and the Internet of Things is growing. There are more and more devices. We are connecting more and more devices to the internet, being the car, being the home appliances, being a security system at home. And the expectation is that soon we will have 20 and 50 billion devices connected to the internet. And with this Internet of Things, obviously we need input from these devices. We need information, what's happening in my home, what's happening in the car. And in order to get all this information, we need some new, reliable, cost-effective sensors. So in order to facilitate the Internet of Things, the MEMS sensors will be necessary in order to provide these signals to those systems. So that's one of the major areas on the consumer side. And also on industry, what's called in Europe the Industry 4.0, the transition of the industry to really data-driven, internet-driven production, where you can produce, control small batches, but with very high reliability at very fast intervals and deliver to the customer. And more information is needed. So in order to control the machines for those production processes, more and more sensors are needed during the production, during the transportation of those devices delivering to the customer. So we foresee for the future also on the revolution on this manufacturing and industry infrastructure that there will be a lot of sensors to be used.
Okay. All right, I think we are arrived at kind of today and tomorrow in your career. What do you do outside of work?
You know, technology like this required quite a bit of dedication and also time. So yes, I have been pretty busy at those times. But family was very important to me as well. So my wife always supported me also during the tough times, and when I had to go and put in special hours and weekends or weeks or some additional trips which were not planned. So she always supported me. We have 2 children. We have 2 daughters. So family, spending time with the family was very important to us, and raising the children. Now both of them completed college. They started this year on the jobs, both the older one and actually the younger one, since we've been over here now for a couple of years in Silicon Valley, and I've been managing the Research and Technology Center for Bosch. She decided to follow us, and she studied computer science at Stanford and just graduated and got a job also in Silicon Valley with one of the major companies. So outside of that, I do have some hobbies. I like skiing and hiking mountains, both in the summertime and in the wintertime. Is always fun. I've been sailing some small boats, but also we chartered some bigger boats and even spent some family time cruising. So both in Europe and over here in the US, we chartered some boats for a week or 2, and the family, including our children and the son-in-law, we spent some time together. So that's sort of the hobbies that we have.
Great. And do I remember right, you told me you're retiring soon?
Yeah, it's
So
sort
what are
of
your
interesting.
plans for that?
As I mentioned before, I started my career as the first industrial job over here in Silicon Valley. After IBM, my first job was in 1983, so that's pretty much 35 years ago, in Palo Alto and Page Mill in El Camino. I'm working at the Research and Technology Center, which is about 3 miles from that location. And after spending all this time at Bosch, building up the technology and bringing it to the market, I spent 5 years over here managing the Research and Technology Center, and I'm now in the fall going for retirement with Bosch. So it's sort of interesting. I started in Silicon Valley. I spent most of the time managing that operation in Germany. I spent then the last couple of years managing overall the Corporate Research and Technology Center in North America, and I'm retiring after that. So started in Silicon Valley, and now it's coming to the end as my industrial part of my life, which is very exciting, and I'm looking forward to spend more time with my wife and the family.
Okay, so you will really be retiring, not like go into some other jobs or so.
Well, I might do some consulting. There are some options. I'm talking to both Bosch. We have a consulting service for managers retiring with a company, where Bosch tries to leverage that knowledge of the people on a part-time basis. So that's an option for me. But there are also some other companies which are interested in my experience of both the German industry and the Silicon Valley technology, and bringing that together. So we will do an extended trip after some very strenuous times. It's time to relax and enjoy that. And so probably in the spring of 2018, I will look more in detail and do some consulting and part-time jobs.
Okay, well, I wish you all the best for your retirement, and
thank you.
Thank you again for this interview. I was very interested.
Thank you very much for inviting me.